crisis ahead. Power consumption in AI centers. AI data centers are consuming energy roughly 4 times the rate that more electricity is being added to the grid, setting the stage for a fundamental shift in where power is generated. Where AI powers data centers are built, much more efficient system, chip and software architectures. The numbers are particularly striking for United States and China, which are in a race to ramp up AI data center. A 2024 report commissioned by the U.S. Department of Energy showed that last year, the U.S. data centers consumed about 4.4% of the total electricity generated, or roughly 176 terawatt hours. The number is expected to increase to between 325 and 580 terawatt hours by 2028, which is 6.7% to 12% of all the electricity generated in US respectively. Figure 1. Total electricity generation versus consumption due to the server storage, network equipment and infrastructure from 2014 through 2028 estimated. Source: Lawrence Berkeley National Laboratory Report. China, meanwhile, is expected to reach 400 terawatt hours by next year, and while those numbers may look comparable to consumption in the US, the International Energy Agency noted that China's citizens consume significantly less energy than their US counterparts. On a global scale, the rate of the consumption is increasing 30% per year due primarily to AI, with the United States and China accounting for about 80% of that increase. Figure 2. Where the electricity is being consumed. Source: IEA. Power is not a joke anymore, said Jean-Marie Bruno, Vice President and General Manager for Hardware System Verification and GMS EDA. Imagine if the data center power consumption in 2028 is 12% of the entire power consumption of the United States. That's insane. We'd have to redo the entire grid. Others agree. Power generation is going to be a big deal, noted Jensen Huang, President and CEO of NVIDIA, during a recent CDN Live discussion with the Cadence CEO, Anirudh Devgan. The reason for that is power grid aren't going to be enough to sustain the growth of this industry, so we'd like to build this industry onshore. And if you want to do that, then we're going to see a lot of digital power generators and all kinds of stuff. So, what can be done about it? There are 4 main target areas, each of which directly involve the semiconductor industry: reducing transmission distances and the number of step-down voltage, limiting data movement where possible, more efficient processing and better cooling closer to processing element or inside of the packages, distance and step-down losses. As with the data, there is a cost for moving electricity. On average, 5% of electricity is lost during transmission and distribution, according to the U.S. Energy Information Administration. What the counterintuitive is that the high voltage lines that run up to hundreds of miles have a lower loss about 2%, then lower voltage lines running over the shorter distance about 4%. Those numbers are compounded by the source as well because different sources have different conversion rates. See Figure 3 below. Figure 3, U.S. electricity flow in quadrillion BTU. Source, U.S. Energy Information Administration, April 2025. Ideally, you keep your voltage as high as possible, which means that current as low as possible, said Eliko Berman, Chief Business Officer and Saras Micro Devices. The losses are the scale of the current times the resistance. So you are losing wind power the whole way, whatever the high intention wires are. You keep stepping that down. That may be 400 volts coming into the data center, and that gets converted to 48 volts for the rack, and then eventually steps down to 12 volts to the point of load. But at every step of the way, you want to generate your power next to the data center to reduce the distance and keep the voltage as high as possible, and bring the voltage close to the endpoint. The trade-off here is the voltage and current. The higher the current, the greater the heat, and nothing is 100% efficient. So as power is moved closer to the package, some heat is generated. That, in turn, is compounded by everything happening inside the package, including processing data, moving into the data back to forth the memory, and the resistance capacitance in the interconnects. On top of that, AI data centers have more data to process, so those workloads require higher utilization rates, which make it more difficult to keep up with the amount of the heat that needs to be dissipated. So, from the high voltage lines to the lower voltage line, then to the PCB, the packaging, and finally the individual die, power is lost at each step along the way. Berman said, how do you reduce the distances? How much voltage can I get as close as possible? What's the efficiency? Am I able to dissipate the heat? These are things the industry is looking at. The industry has a big role to play here. We have too many steps to do the existing infrastructure, where we had so many intermediate voltage levels, said Andy Heinig, head of the Department for Efficient Electronics, and Fraunhofer IIS Engineering of Adaptive System Division. For sure, we can save a lot of energy here. What we also see is a need for the processors and power regulators to work together. Currently, power regulators are not intelligent. They only follow the current coming from the processor. But the processor knows what they have to do in the next cycle, and they can inform the power converter that a huge jump is coming or that something is switched off. So there are certain points where we can co-optimize the processor plus the voltage regulator, and reducing the number of intermediate voltage levels will help. Moving data. Another challenge is to architect systems so the data is processed closer to the source. That reduces the amount of data that needs to be moved, but alongside of that, the distances that data must travel need to be reduced, as well as this is one of the key drivers behind 3D IC packaging instead of running wires across SoC. Components can be strategically placed vertically to reduce those distances. That improve the performance as well as the amount of power needed to drive signals. One of the biggest challenges for our customers at the moment is wire length and the designs, such as Andy Nightingale, Vice President of the Product Management and Marketing at Arteris. Multi-die is a separate challenge, but on each monolithic die, preferably goes through to multi-die. Getting the wire length down is critical to power. One aspect looked at is congestion. We've got heat maps in our design analysis as well then look at congestion, because that's a key point where a number of wires meet together at a width switch. We work with the floor plan as well, where we visualize the physical design so we can move the switches out of a congestion point and still work with the flow plan to reduce the heat dissipation in one area and power congestion as well. This also will require a mindset shift because power still takes a backseat to performance in AI data centers. But if no more electricity is available, or if the price of the electricity skyrockets, then the AI companies will have no choice but to get serious about power. The emphasis on AI design these days is still very much performance, which means that wire power is really important. It's still a secondary concern to getting the best speed and performance out of these chips. Says Mark Sweeney, Director of Product Marketing at ANSYS, now part of Synopsys. There's always a power performance trade-off, and that's fundamental. So if you really want to lower the power, you'd have to lower the performance. Going down where low helps. That lowers the power. The other thing is that most of the power is in the communication between GPUs and the different elements. But even the backplane in the data center, NVIDIA came out with the co-packaged optic networking just to reduce the power in the communication with the lag and between lags. Solving these issues requires changes across the entire chip industry. You start on the chip, and the chip is very power hungry, and you want to build an LLM, and you've got to train these things. Said Gmail, Bruno. You train it by adding multiple functions and scale, but if you add things up, starting with a single element, that is very power hungry, then the entire system is extremely power hungry. If there is a digital twin, you need a tremendous amount of power to compute that digital twin as well. But that isn't the problem for the industry. It's a problem for the whole world. More efficient processing. The good news is there is some obvious low-hanging fruit. There is a 20% power tax simply because of lack of visibility, said Mo Pfizer, President of CEO of Mobilus. For example, say you design a chip for 500 watts at 2 gigahertz. By the time you're done with the system level test and you're ready for deployment, you'll find that all of those power systems were constructed with different goals. So now, if you want to stay within 500 watts, you have to crank the frequency down by 10% and 20% is basically a throttle. And this only gets worse with the chiplets because now you have the same thing, but you multiply it by the number of chiplets that you're dealing with. Each chiplet could have a different process corner, or it could be a different process. That's part of the picture. There's additionally 20% to 30% gain to be had by installing more visibility from the chip to the system and all of the way to the data center, Pfizer said. And both of these compound, so it's not one or the other. The reason is that the chip designer is concerned about risk. Hey, I don't want the chip to ever fail. So they are gonna overmargin with the redundancy. But in deployment, when you're designing the data center, you are not designing for the maximum workload. You're designing for peak workload. And the reasons for that is workloads and software are changing much faster than the chips. It's impossible to test a chip with all the combination of workload that you will see the field because the workloads and the motors and the transformer and agent are challenging so fast. So you have to margin than it. The data center capacity is 30% over provisions compared to what you will see in the max load. Understanding how semiconductors will be used is critical to this equation. As well, just adding redundancy and guard banding everything for worst case corner cases increase the power needed to drive signals through extra circuitry and the amount of time that they need to be dispatched to the resistance, capacitance, and the wires. Normally, you plan for worst case scenarios, said Noam Broussard, Vice President of Solutions Engineering at Proteintech. So over time, you plan for the worst things that can happen at a specific temperature or variable. If you can meet the spec, then everything is okay. But now we are running higher workloads that continue to increase with over time, and we are expecting chips to last longer. With artificial general intelligence, AI algorithms, chips are processing a tremendous amount of compute. 4 chips in a data center that now is expected to last 8 years, instead of a historical 4 to 6 years. It will have to be able to handle that increase in workload. But planning for what will happen 8 years from now is just not feasible. That planning becomes even more difficult in the context of accelerated aging and added stresses. Thermal, mechanical, usual workloads running at full bore for longer periods of time. It's very hard to use one motor that factors all of these variables, and if you do, you're gonna be higher, more provisioning, Broussard said. The only way to keep power consumption in check, expand the product lifetime, and maintain reliability is to dynamically adapt to the ever-changing individual power needs of the device over time. Moore's law, plays a role here, too. While the improvement in the processor performance at each new process node are diminishing, so the improvement in the power consumption are projected to be substantial, as much as 30%, depending on process and foundry. As with any new process, those numbers can vary significantly by architecture and workload. Cooling. The rule of thumb is the data centers pay for power twice. The first time is to power the racks of servers and storage. The second time is to cool them so they don't overheat, and that's becoming the bigger problem because the dynamic current density is increasing along with the utilization of AI servers. It takes more processing to train large and even small language models and to power generative and agentic AI searches. That, in turn, increase the utilization of various compute elements that they are running at full but for longer periods of time. The power override for cooling is about 30% to 40%, and there's just gonna be liquid cooling without chillers. You can cut that in half, said Cyrus Bergman. If you add chillers, it goes right back up. There's an optimization game that needs to be played here. The pivot point in the equation is availability of wave water. Running water in the closed system requires cooling. Using the local water supply does not. But according to the Environmental and Energy Study Institute, a large data center can consume about 5 million gallons per day, which is about what a town with between 10,000 and 50,000 people would consume. Two alternatives are direct cooling of the individual die and emergent cooling. Direct cooling can involve the microfluidic channels, an idea first proposed by IBM back into 1980s and later abandoned because it was too difficult. But as the thermal density increases, chipmakers may have no choice but to utilize some type of microfluidics. Still implementing this approach adds structure and manufacturing challenges. The idea is well understood because water cooling has been used for more than a half a century, but implementing it inside a package or chip closer to the transistor remains a challenge. If you're looking at cooling technology, there's heat transfer efficiency, which tends to be looked at from a thermal distance perspective, and adjunct fluid temperature in a general sense, explained Rajiv Munjia, senior principal engineer at Intel and leader of the company Thermal Core Competence School. But if you want to look at it from a thermodynamic perspective, it's not junction to fluid inlet temperature. Its junction to fluid exit temperature. Basically, the higher you can make the fluid temperature as you exit the package of the packaging area, the easier it is for everything downstream to manage from the heat transfer perspective. That affects the overall efficiency of your cooling plant, your chiller, and all that stuff. This is a consideration in stacking dies. When we get to 3D ICs, you might need to get a fluid within the structure itself, like a silicon microchannels on the backside of the die. Munjia said, a benefit complex ratio. You could create with this type of plate sitting on the backside, but once you have enough volumetric heating within 3D stack, imagine a cube of some sort You no longer can conduct the heat out through one side of the silicon. You have to pull the full heat from the inside of the silicon in some way. At the end of the day, some exotic mechanism is going to be required because you're generating so much power within the volume of silicon as opposed to just on one surface. Emergent cooling, in contrast, involves putting an entire surface into inert liquid. The challenge here is the same as the microfluidic. The heat needs to be drawn from the inside of the rag out and is spreading the thermal and load inside the packaging. To external cooling bath is more complicated than it might sound. It requires understanding of where to place components in a package, potentially thermal interface materials, and heat channels from digital logic to outside of the package. It's also possible both these approaches can be used to get the sharper DC heat, which could allow for even higher transistor density and even large demand for electricity. Money and resources. None of this is lost on the chip industry to move forward and continue growing at least as fast as today. Two related issues need to be addressed: sustainability and cost. Those ultimately will determine the speed of deployment of AI data centers, the amount of processing that can handle, and what changes are needed from a transmission standpoint from a chip, system, package, design perspective. Sustainability comes in the equation all the time because there's many decades worth of pressure on a corporation to use our natural resources better. Say Mike Ello, CEO of Siemens Digital Industry Software. That's where we're headed. With semiconductors as the backbone, that's gonna help a lot of industry. If you look at the power consumption from data centers, where we are headed is unsustainable. For us, the challenge is how to put 4, 5, or 6 times the computer power into the same power profile that already used for the data center. Business basic figure into pictures as well. At the end of data is total cost of ownership. Say the Intel Mongia. Whether it's a large language model that you're creating or an inference you're trying to generate, there's capital cost and operating cost to do that. Thermal comes into capital cost as well as the operating cost. So what is the balance? What is the ROI? What does it cost to upgrade a liquid cooling solution? Because those historically are more expensive than a cooling. Although AI data centers of AI solutions are predominantly liquid cooled. For us to build it, you need to get more out of your package, meaning more inferences or more performance on generating your language models, and thus reduce the operating cost over time. Conclusion. To put this in perspective, consider that the Hoover Dam in Nevada generates about 4 trillion watt-hours per year. The Palo de Bermuda nuclear power plant in Arizona generates 32 terawatt-hours per year, and the Three Gorges Dam in China is expected to generate 90 terawatt-hours per year. But between 2028 and 2030, given the current rate of growth, AI data centers power demands will increase by $350 terawatt-hour, which is nearly 3 times as much energy as all of those generating facilities combined. No single change will shrink that gap. For the semiconductor industry to continue growing at a current pace, it will require changes from the grid on down and from the chip up. And even then, it's not clear if that will really close the gap or whether it will help. It will simply enable AI data centers to grow even larger. Okay, today I read this article, Crisis Ahead, Power Consumption in AI Data Centers. Thank you for your time. See you next time.